discussion is in English because we have a special person, a special scientist in this occasion. So let me start the presentation of the scientists which are sitting down just in front of you for participating in this round table. And let me start with our guest, which is Professor Ben Feringa. He's a professor, distinguished professor in Groningen University in Holland. And well, he was originally educated in this university, and but then was for several years, 6 years I think, was working in Shell company, first in Holland, and another 3 or 4 years in UK. So he was also is one of those rare scientists who has had a long stay in a private company. You know, so this gives you an approach which is very appropriate for many purposes. And then he has received many awards, very important awards, but let me go to the top of them, which is in 2016 he received a Nobel Prize together with Jean-Pierre Sauvage. Last year he gave us a lecture, but it was on 2D. It was on, you know, from Strasbourg. He couldn't come because at that time it was a little bit risky for him. And Fraser Stoddart, that was the third, and they got for the design and synthesis of molecular machines. So now is a very good opportunity to discuss on this topic. Mm-hmm. And in addition to nanoscience, which is the main reason for his stay in this occasion, he has been engaged in many other topics, catalysis, biological and biomedicinal aspects as well. So there is a polyhedric vision of many aspects in science. Mm-hmm. So Montserrat Colillas is a professor, is associate professor at the Faculty of Pharmacy in Complutense University, and she was in this summer school. She was mainly dealing with the topic of biomedical applications. So, and drug delivery has been another of her topics. Continuing over there is Professor Rodolfo Miranda. He is a physicist. You see that this is nanoscience, is community, physics community and chemical community are, I would say, important, but also biology, engineering, many others, mathematicians as well. So, and he is currently he is full professor in Autonoma University. And currently, well, he was the founder of the India Nanoscience Institute, and since the beginning he has been the director of this important institute. That he will tell us something about this institute having almost 250 scientists today. Mm-hmm. And topics, mostly he was one of the pioneering scientists in Spain on dealing with STM equipment. So this is the tunneling effect microscopy, and then many others. Mm-hmm. And last but not least, Andrés Guerrero. He is full professor at the Department of Physical Chemistry in Faculty of Chemistry at Complutense University. He is very expert in working on nanoparticles and applications of biophysical application as well, Andrés. And we are developing a joint project at Complutense University related with is REACT, related with how to prevent new pandemics in future. Okay. So these are our four super speakers, and what I would like to ask you is just to start in 2-3 minutes, responding to the question. Yeah, this is Ben presentation. So the idea is to take 2-3 minutes to introduce the topic. Okay. So please go ahead.
Me?
Yeah.
Okay. Let's see if this works. No? It's okay? All right. Now, first of all, thank you very much for the introduction and for having me here. It's great to be here, you know, at this very famous place and to see you all, and I look forward to our discussions. I prepared a few slides, actually, you know, as an introduction, because you were not at my lecture this morning, and tomorrow you will be at the lecture, and which is in this hall, I understand. But, you know, I'm a molecular nanoscientist. So, in fact, people ask me, you know, what are you doing? And I say, I'm a molecular engineer. We like to design molecules, you know, and machines at the nanoscale. So, in the art of building small, what we do is we design molecules, and particularly things that move, yeah? So, switching and motors, and I was discussing this morning at the Institute. But I want to put it also a bit in the broader context, because you are at the beginning of your career, and you will all face the following problems. You know, I'm a chemist, and chemistry is the creating science, and I mentioned it this morning, and I want to mention it explicitly again. We have the big challenge of making sustainable process in the products in the future, yeah? Green design. Reinventing materials, it's really important. Changing the face of our chemical industries, yeah? And from trial and error to molecular design in the medical, biomedical, pharmacy, medicine, techniques, etc. So many fundamental questions for all of you, and many challenges and perspectives for industry and society. And here, nanotechnology, insight in systems, molecules, and materials at the nanoscale will play a crucial role. And why do I say this? Let's take the example, you know, of biomedicine, nanomedicine. Look at your cell, yeah? It's a complex machinery, you know, a system with all these nano compartments, nano components, all these machines, etc. The fact that I can speak to you, yeah, you can see me, this is all molecular nanotechnology. So the start, I want to say a few words about my start. The start is always difficult, eh? The first steps, yeah, on the journey. And you are still at the early stage of your career to make the first steps. And this is always a point of uncertainty. And when I had to write my own grant, yeah, I asked some famous professor, and he said, choose an important problem. I don't know if I listened carefully, yeah, but I decided to work on molecular information storage, 0101, yeah? And this was me apparently, this is what I found on internet recently when I started my career, just after my PhD, when I came to the university. We chemists are lucky, he chose academia instead of becoming a rock star. I'm sorry, I cannot sing, so I made the right choice. And apparently I said that those days, yeah, the beauty of chemistry is that I can create my own molecular world. And that I've ever done ever since, yeah? So this was apparently me, you know, a little bit older than you know, after my PhD, when I finished. So I designed molecules, that is what I did most of the time. And so I designed a motor, and we work on molecular motors and machines, yeah? Like the windmill that I showed in the first slide. And I enjoy very much to work with the young talents and with the students. And my first grant application, as I mentioned already, I got this advice, yeah. I had big questions like we all have, what to do, you know, how to distinguish yourself from others. But I wanted to work on this molecular nanoscience. And yeah, to give you an advice, yeah, what I learned over the years, guiding a lot of young people, discover your talent. Follow your dreams, be confident, discover your energy, what is your passion, and discover your limits, eh? How high can you set the bar? Sometimes it's really rewarding to do something difficult. Don't always take the easiest way. It's an adventure for all of us, yeah? But this is what I experienced. And if I give you real advice, of course it's always good to keep the eyes open and listen to the senior people, you know, but the most important, follow your dreams. And with that, I would like to conclude this small introduction. Thank you.
Good evening, everybody. I would like to make a brief introduction to try to create a dynamic discussion after the honor that we have of Count with Ben Feringa. And today we are going to discuss about nanoscience and its impact, scientific and social impact. So first of all, I would like to highlight the discovery of synthetic molecular nanomachines by Professor Feringa, that is here with us. And now a brief view about nanomachines that tomorrow you are going to be able to receive the talk of Professor Feringa. Here we have different types of nanomachines, and I would like to connect the discovery of this type of nanomachines with nanomedicine, which is the main goal of my topic this morning, my talk. So, as you know, the nanomedicine is the application of nanotechnology to the discipline of medicine. That means that it's the use of nanoscale material for the diagnosis, monitoring, control, prevention, and treatment of diseases. So, in this context, my question is, molecular machines and nanomotors are, what's the potential in medicine, in nanomedicine, reality or science fiction? This is my question. Mm-hmm. So we have read books, or we have even films showing how nanorobots can act as small surgeons and artificial life. This is the promise of the tiny machines. Two of the major concerns of global society, according to the World Health Organization, is cancer. I talked to you this morning about this. The multi-drug resistance remains a big challenge, and infection, mainly bacterial resistant. That is going to be one of the foremost reasons of death during the next coming years. So in this context, I have been reading a lot. I had the opportunity of reading research papers inspired in your pioneering contribution to this field. And I have been reading that it's possible to design molecular machines that open cell membranes. That could be applicable to the world of cancer, because it's possible to use these nanomolecular machines to act as nanodrills, to create holes into the cells, and to finally lead to cancer death. Another strategy applied to infection is the possibility to design like activated molecular machines to kill antimicrobial resistant bacteria. This is another tentative basic research in this context, how molecular machines activated with light can be applied to the development of antibacterial therapies with a mechanism of action totally different to that of conventional antibiotics. Mm-hmm. It is possible, this is one of your papers, it's even possible to administrate an antibiotic that is not effective until you apply an external stimulus, such as light, for instance. So another thing that I would like to ask Professor Feringa is that, taking into account the long-term in the general pipeline for the development of therapeutic nanomedicines, the main question remains if we are living in reality or science fiction regarding the translation of this type of nanomolecular machines to the clinic, to the patient, from bench to the bedside. That, for me, could be very nice to to hear your opinion and to know what's your perspective into this topic. Thank you very much.
Thank you.
Okay, thank you. Please, Rodolfo, go ahead.
Well, thank you, Nazario. Well, nanoscience and nanotechnology. Well, nanoscience is about discovering new laws. Matter behaves in a very different way at the scale of the nanometer. All properties of materials are different, they change completely. All properties means all mechanical properties, electronic properties, magnetic properties, optical properties, even reactivity, changes when you take a piece of material and you make it as small as something of the order of a few nanometers. Now, we physicists are always trying to find universal laws that are applicable to any type of material given a certain very simple conditions. So science at the nanoscale is obviously a very interesting playground for this type of approach, because we have found already many laws that are universals and completely different from the behavior of the material at the larger scale. Such as, for example, all collective phenomena, and collective phenomena are typically magnetism or superconductivity or many others, depends crucially on the dimension of the system. So when you go to a very small system, for example, critical temperature, the Curie temperature for a magnet, for example, decreases continuously and very strongly when you go to smaller and smaller pieces of material. When you go down to materials of the order of 1 atomic layer thick, again, the physics is completely different. One of the main examples of that, very famous, is graphene. This material has fantastic properties, but let me mention just one. Graphene is a piece, as you all know, I mean, it's a single layer of graphite, so carbon atoms in an hexagonal, well, in a honeycomb structure, to be more precise. In graphene, in this single layer of carbon atoms, the electrons move as if they will have a mass equal to 0, which means that they move and they carry current and signals in graphene at a speed that is only about 300 times smaller than the speed of light in vacuum, which means that electrons in graphene can move faster than light in most materials. It's something really amazing, and it's because of this funny law that apply to this type of two-dimensional materials. And there are many other examples. So nanoscience is about that, and obviously it's a field where there is a very clear overlap between physics, chemistry, biology, medicine, and engineering, because if you work with a single object of that size, if you work with a single molecule, what is that? Chemistry, because it's a molecule. Physics, because you are looking at processes at the atomic level. Biology, if it's a molecule of biological interest. Well, it's science. And science at that level also has a lot of fun, because you work normally with other colleagues, if you are lucky enough to work in a place with interdisciplinary teams that know things very different from the thing that you know. So if you are working on a physics department, all your colleagues, even if they are extremely good, they know more or less the same type of thing that you know. If you work in a chemistry department, more or less the same. But if you work in this type of environment produced by nanoscience, I can tell you, first of all, there is a lot of fun. So you really learn every day from the other colleagues that know much more than you on certain things. So that's an interesting point. And then, surprisingly, many of the things that we learn at that small scale in conditions that are very far away from reality, in ultra-high vacuum conditions or in a very low temperature, or in conditions really that one might think that there's no application for that. Surprisingly, many of these things do find applications in our world. And there are many examples of that, and that is basically nanotechnology. Nanotechnology is already all around us in many devices, in many things that you can buy and you have probably in your pocket. the transistor in your, the smallest transistor in your last mobile phone has a gate length of 2 nanometers. So it's 20 atoms from one place to the other. So that's really nanotechnology in your pocket. It started many years ago. In fact, we started more than 30 years ago having the first product of nanotechnology in the market. Initially, the first one was probably the reading head of the magnetic hard disk. All magnetic hard disk in the world and the computer use a magnetic reading head that has a thickness of a couple of nanometers. And that was the discovery of the giant magnetoresistance years ago. So there are many things around. I mean, essentially, if you can summarize, we can think that in this century, probably almost everything around us, from the way we harvest energy, we process information, we store whatever we use for the buildings, the way we will heal our sickness, or even in our dresses, will contain elements of nanotechnology in one way or the other. One, in some cases more, in some cases less. So it's a world also in which the distance from the basic science to the application is relatively small. In terms of years, maybe a few years, but it's something that one in the career can have, can start with something that is very basic science, start with something extremely applied. So we are trying at IMDEA Nanociencia, the Madrid Institute for Advanced Studies in Neuroscience, but I have the honor to be the director, to explore limits in basic science from all the limits of this nano world, which comes to go into ultra high resolution in space and in energy, so processes that occur at very short scale in space or at extremely small values of the energy, but also processes that occur at ultra fast time scale. We were discussing this morning that many processes that occur when the light interacts with organic materials take place on a range of processes that occur from seconds to femtosecond. And in principle, you don't know which one is controlling the behavior of your organic device in reality. So there are a lot of things there in this ultra-fast regime of time that is also one need to explore. And all of that is to be used, let's say, in a number of what we call research programs that cover a wide range of things, from harvesting energy to nanomedicine. There are a lot of applications of nanomedicine carried out at the Institute that are already at the hospital. They are used with human patients in some cases, to nanomagnetism, or to a number of quantum technologies. All of this is done in this environment of this funny institution, which is not part of a university, it's not part of a National Research Council. It's a private non-profit foundation with approximately 250 scientists in this moment. And it's a place in which, of course, you are all welcome to come and try to follow a career competitive at the international level that can give you the first step in your scientific career. So you are very warmly welcome if you want to come by.
Now it's your turn, Andres, and after this exposition about your students can decide the topic. So you can ask questions, specific questions, and okay, so Andres, please go on.
Yeah, so thank you very much for being here, Nazario, and it's an honor to meet you, Professor Feringa. For instance, thank you very much for the inspiring words and sentences that you wrote there, because I don't have the answer for some of them. I am still looking at, so it means that I think that they are open questions not only for you guys, maybe that you are at your first period of your degree, but also for us as human beings and as scientists, because many of them try to focus on what do you want to do, where do you want to put your energy and your input. I think that they are very, very inspiring sentences and complicated to be answered sometimes.
For me too.
Yeah, regarding the impact of the nanotechnology, I think that there are now, as we mentioned, that there are many applications already, or many devices that are built up with nanomaterials, with nanoparticles, and that we are using in the day by day, everyday life. There are, I think that, for example, organic synthesis, using different strategies, we can synthesize almost every molecule, every complicated molecule that is in nature, and you can find it. And it's possible to synthesize. Sometimes it's quite difficult, especially for people that are working with natural products. But it's possible to synthesize and to get molecules with defined properties, with defined structures. From an inorganic point of view, I think it's also quite similar. So we can create nanoparticles of different compositions, quantum dots, nanoparticles, iron oxide. We can control the morphology now, the size, the monodispersity. So the improvements in that sense are amazing. Maybe in the future is the interface. The interface that Emilio was talking this morning about the interface, right? How we can connect molecules and in organic systems or in organic surfaces in order to create or to find new properties, to enhance molecular properties, to enhance nanoparticle properties. How can, for example, we can increase the optical efficiency of a dye in an OLED, for example, in your smartphones? How can we get a light that is more white? How can we, or a black that is more black than now many TVs? No, this is what they sell: a quantum dot TV. The black is the most black TV, or the most so. And I think in this interface between the molecular regime and the nanostructure and nanoparticle, there are many things that we have to do and to develop. For this, of course, we need chemists, we need physicists, we need biochemists, biologists. And one question, for example, that I would like to ask to Professor, how can, for example, we could in this field of molecular motors that you connect to a nanoparticle with a certain specific properties, electric properties, optical properties, how can this combination can enhance or can induce new properties that cannot be obtained in other way? And the combination of both, I think, it's part of from my small point of view, I would say, it's part of how the nanotechnology is going to be addressed or how to be pushed. And yeah, there are many examples. For example, with the COVID vaccine that we were talking this morning, COVID vaccine is a real nanotechnology product. So, but it's important that all this, what we call colloids, maybe 30 or 40 years ago, now we call nanoparticles. But it's a colloid, it's a micelle, it's a basic system. It's a basic system that is well known since many years. My professors already, they study and they characterize this with conventional techniques like DLS or whatever. So sometimes the things, they come again and they can be used again, and so we have to be open to the old research. The basics are very important. So don't focus only from I think in the last research, in the last papers, in the last, but also read papers that maybe they were written 30 or 40 years ago, because they are still active, they are still useful, and you can learn many things from research. We were talking this morning about the Faraday paper, right? Relating the interaction between gold and so Faraday, nobody cited Faraday during the 20th century. Just at the end, when nanotechnology grew up, suddenly this paper was like something like some very paradigmatic study. So I think we need an open mind. We need to learn from the past. There are many things in the future to be done. and this combination between the molecule and the nanostructure, I think we can get many new properties. And this I finish
Yeah.
Maybe Emilio or Nathan.
Interact. Please don't be shy. I know there's a Nobel Prize with us today, but just be as active as you were yesterday.
Thank you so much. This is it's a pleasure to be here. Maybe it's really difficult to start speaking about nanoscience in front of the best researchers in the world. Today we had a really nice talk about nanotechnology, about nanotubes and the rings that Emilio was speaking about, nanotubes of graphene. My question is maybe is a little dreamy, I guess, but I would like to ask, when we are speaking about drug delivery, maybe a quantity, the amount of drugs that we want to introduce to the body is a problem, or how we should do that, or the limitations. I was thinking graphene, nanotubes, graphene mostly is conductive, and nanotubes, is there any possibility to functionalize this ring? I guess that was a metal organic ring around nanotubes. We could functionalize with another material that would be another organic frameworks. That would be pros. So we introduce the drug and we put these nanotubes with a lot of rings inside of somehow like a electrical
Field.
Institution electrical to do some superconductivity. We can do the delivery in this phase or not.
Difficult question.
Well, difficult to understand.
Okay, I can say something about it.
You're okay with it?
Yeah. Sorry? I'm not an expert in nanotubes, so modification of nanotubes is possible, of course. But if you talk about drug delivery, I mean, next to me here, he can talk about that. But of course, there are many different approaches, you know. First of all, for many years, people have been working on polymers, polymer capsules, polymersomes, and these kind of things for controlled drug delivery. We ourselves work on self-assembled systems, so supramolecular capsules and so that can encapsulate small drugs, and that then can go inside the cell or towards the cell. More important is, of course, how to target the cell, you know, so you have to put something there that anchors. So for instance, with the nanoparticles, you know, you can put oligonucleotides there, you can small ligands that bind to specific proteins, etc. With the nanotubes, I think there are opportunities but you have also take into account that you have to think also about toxicity. When you have compounds, you know, you bring into the body and living tissue, how toxic is it? What kind of other effects might they have? Tomorrow, I will give a talk, you probably will be there, and I will talk about a nanotube that we built a submarine. You know, so he was talking about science fiction. So we decorated a nanotube with 2 enzymes, and then it propels autonomously. So now the next step is to use it to deliver something, you know, yeah? But that works, yeah? So wait till tomorrow, yeah? And then you can ask me again a question. But maybe my neighbor here can talk about a little bit about the approaches that are followed, yeah? Beyond nanotubes, because I think there are many other interesting systems.
Yes, thank you for your question. I don't work with nanotubes, but I think that, as Professor Feringa says, it is possible in one approach, it's possible to combine well-known self-assembly structure such as polymer nanoparticles, polymerosomes, nanoliposomes, and so on, with carbon nanotubes or graphene nanosheets. It is possible to combine soft materials with carbon derivative nanostructures in order to try to obtain synergistic effects due to the combination of electrical properties, conductivity properties, and so on, with the inherent drug delivery behavior of the soft nanoparticle. Nonetheless, it is possible. I think that there are something published in the field of using carbon derivatives acting pore capping as nanogates of porous materials that can host the drugs inside, and so on. And I think that we have to look for strategies, dual strategies, combination therapies by combining an antibiotic and photothermal effect, near-infrared photothermal therapy, photodynamic therapy, and so on, with chemotherapy or antibiotic therapy. So this is a promising approach, I guess.
I think the way that you regarding the question toxicity is a big deal. So we cannot use whatever thing for whatever application, or because your idea is that this system could be biocompatible, but later, as we saw, for example, this morning, you try to use a nanoparticle and you induce the disease even faster, right? So in the case of maybe this kind of organic nanomaterials, more than use these particles in order to control the delivery or the release of a drug, I could imagine something like something imprinted, something that you can maybe imprint, or you can connect to your skin, and you can. There are devices, in this sense, with an electrical control, with some kind of sensor, can inject or can introduce the drug, or can introduce cations, for instance, or whatever that your body needs in a skin, in a topic way, more than maybe to introduce in your blood, because maybe, as we saw this morning, the protein corona, as soon as you put something in your body, suddenly everything is surrounded by proteins. The body try to protect itself, and at the end, what you have is a corona of proteins, and maybe the particle is not active anymore. So for this kind of material, maybe it's more logical to think about something imprinted in your skin or something like that. Yep. Good.
Or maybe
No, maybe.
No.
Somebody else.
Well, actually, I was not thinking to use the nanotubes and doing the delivery inside or through the tubes. I was thinking to use them as a machine, like the exactly things that Emilio was speaking about. There is a ring around, and we use it as a track that some organic compounds or functionalize something fastly introduced to some. For example, there is a part like a cancer cells inside, and we know that, for example, this is in the arm or something. We introduce these tubes with 10 millions, 20 millions, I don't know, because I asked if there is a chance to move the rings in through the.
You mean a startup type system where you have rings along a string, Rodexans and so, or what David Lee does. Yeah, but to make it compatible with a cell, that is different dimensions. You have to think about that.
And the
concentrations, the dimensions, and then how does the body deal with this? Because, for instance, we work on bacterial resistance and bacterial infections, and the first thing bacteria do is nicely form a biofilm. And then if you have a strange object, you form a biofilm, and then it's very difficult to get through it, because it's very difficult to penetrate biofilms. So to give you an alternative, to your approach, is we do photopharmacology, you mentioned it, to take a drug that you activate on the spot. yeah? Or you make nano capsules with protein channels that you can open and close. I was discussing this morning on the spot. I think nano machines, you know, nanomotors, James Tour uses it also to drill holes in cell membranes and so. I think that holds probably more promise, you know. But who knows, nano needles, you know, and then you can move something, might also work.
I think if carbon nanotubes, the main problem would be asymmetry. I mean, all the machines that Ben makes, they are asymmetric for a good reason. Tubes are very difficult to make asymmetric. So pumping in one direction is going to be at least difficult.
Yeah, but you can use Janus particles. People work on Janus particles where they make different sizes, you know, one side or the other. For propulsion systems, that works, you know. That if you look at the work of Sen, for instance, you know, with his propulsion systems and so. So there are approaches. So I wouldn't say no, but I'm a bit skeptical there, yeah? Because I see other approaches that make more sense, yeah?
Okay, yeah, go ahead, but please, short questions, I mean, as possible, because Tempus Fuji, and you know, and if possible, quick
Sure.
answers, relatively.
Short
Okay.
question, short answer.
Okay. So please, this is because it's to speed up the analysis.
Yes, I'm going to try to make a little debate here.
And remember, this is
Around
scientific, but also social.
Yes, that was
Okay,
my
so let's fly our imagination.
Okay, well, first of all, I'm really glad to be here with all of you participating in this round table. So my question is a bit general for all of you. It's like, as you are researchers from public institutions, or maybe you have appeared or participated in private institutions, how much time do you think that the public research or the basic research that you are doing in your day takes to appear in the society, to make some changes? Or because I think the speech was about nanoscience and society, so how much time or how many years it takes to appear in society? And in addition, if you know about some maybe systems or nanoscience that is going to be relevant for the society in like 5 years, 10 years. Thank you.
You mean applications or?
Yes, because you are from different maybe.
Well, I mentioned several applications that are already in the market. That there are.
Yes, so, but my question was more about how many time does it take to basic research like
I'll tell you.
we all do in.
I'll tell you. Typically, according to our experience, I will say from the basic idea to something that is in the market or in an hospital, it takes 12 years to say a number, right? We have a good example of that. We developed a technology based on magnetic nanoparticles to kill selectively cancer cells by magnetic hyperthermia. So magnetic nanoparticles that can be functionalized in a way that recognize the surface of the cancer cells and enter preferentially into the tumor cell. And then you apply an external magnetic field, very small in intensity but very high in frequency, like 100 kilohertz or something like that, and a few milliteslas of intensity, so really a small, tiny magnetic field in that sense. The magnetic field hit the nanoparticle, which in turn hit the cancer cell, and by the time you reach 42.8 degrees, the cancer cell dies. It took a little bit more than 10 years from the first idea to go all the way to the first clinical trials with human beings that have been carried out in March this year in Valdebron Hospital with 10 patients by now, to go all the way from the games that you play in the lab through all the animal models, and this in the case that things go well. There could be in many cases that the thing go wrong somewhere along the way and will never be something useful in that sense. So it takes some time. And then you need to have a sustained support from whatever, public institution, private institution, whatever, because it takes a long time. That's a reality. And in that case, because it was accepted by the ethics committee, that we are doing something that was called a medical device and not a medical drug. If it will be a medical drug, it will be much longer, the period of time, in that case. In some of the cases, it depends on how the market will proceed. There are some other examples I was mentioning to Ben this morning, showing this thing, for example, with the with the magnets that do not use rare earth in the composition. In this case, there was a strategic need not to depend on the supply of rare earth, which are all strictly controlled by China. So there was a strategic need, and then all companies were prepared to introduce this thing very fast in the market, and then it took 8 years, which is about the same. So that's the order of magnitude.
And you should also, is correct, it critically depends also on what area you are, yeah? And it critically also depends upon if there is a societal need or people see it. Realize that the lithium battery, yeah, was discovered, John Coudenhau and so, he just passed away. He got 3 years ago a Nobel Prize, I think, for the lithium battery together with his Japanese colleagues. The chemist, he was a chemist, invented this in the early 80s, early 80s, the lithium battery. Otherwise, you would not have a smartphone, and we would not have electric cars. But at that time, there were no smartphones, and there were hardly, people were not even thinking about electric cars. But so it took 30 years, and suddenly, yeah, everybody wants to have batteries, and good batteries, and fast batteries, not for the, for the smartphone, of course, but also for the electric cars. So that's why there is so much battery research going on, certainly, you know, it has skyrocketed. And he realized that the smartphone, basic discoveries were done 70 years ago, okay? But on the other hand, I mean, if you are in the biomedical field, you are absolutely correct. The standards are so high, and it's so many steps have to be taken before you can go into a patient or whatever. But on the other hand, we work on a new chemical click reaction. Can you give you an example? That reaction normally took 4 hours at 80 degrees. And now we have a reaction that goes at room temperature, 5 to 10 seconds. And why is this so important? Because we use it now together with our friends in nuclear medicine to introduce carbon-11, carbon-11, the isotope, into drugs. Because in the PET imaging, I'm sure you heard about positron emission tomography. You read the big, where you go inside, and you insert your camera, you know, and they make a scan, and they find tumors. Now, carbon-11 is not used so much because it's very difficult to get it in, because you have to get it from the medical cyclotron, You have to do the chemical reactions, you have to purify and get it into the patient, injecting, within 1 hour. Now, you can never do this if your chemical method takes 4 hours at 80 degrees, You can forget. But now, when you have it 10 seconds at room temperature, so now we developed this method, and the guys in the hospital developed it, and now it's used in the patient, because they can do the whole chemistry in 20 minutes, purify it, and within an hour, they inject in the patient. And this was done within 2 years, because it was already a target that they used for detecting brain tumors, so they could shorten all the procedures. And so it can go very quick, but it completely depends on the case.
Okay, next question.
Hello. I wanted to also go back to this issue of the time it takes from the research of the laboratory to reach the society. Whether maybe that's, I don't know if it's being done or maybe it's too soon to be done. Some sort of standardization in the nanotechnology industry, in the sense of, as if now if you want to build a computer, you have a graphics card, you have a processor, and you have some elements that you can kind of like combine together, and you always use the same elements and they work together. Whereas maybe now for many of the applications you have to go all the way through from the beginning of the idea to the final application. And maybe if there is some sort of way, or maybe what's your opinion about it, regarding if you can use things that have been done before in a sense of like a modular building of the nano devices or something like that?
Well, you want me to answer that? Well, yes, to a certain extent. You always build things on top of the previous knowledge and technology that you have developed. So in that sense, you are not always starting from zero. So, for example, the technology that I also mentioned this morning to them with the trying to make, making in fact, nano detectors of the magnetic field from the brain for people that have a spinal cord injury. So they have cut the spinal cord and they're paraplegic, and you want to restore the connection between the brain and the legs. You need to, first of all, to detect the magnetic signal coming from the brain, then obtain an electrical signal from that, and pass the electrical signal to the leg. And back the signal from the leg, again, detect the magnetic part, convert it into electrical signal, and then send the signal to the brain. Now, we have taken full advantage of the fact that in the 80s, it was discovered, this way of arranging magnetic and non-magnetic materials, so to detect by giant magnetoresistance, exactly the same effect that was used, the same technology that is used in the magnetic reading head. And if you tune a little bit this type of technology, then you are able to detect the very tiny magnetic field from the brain, even in room temperature, in standard conditions, without any type of shielding. So the detector is extremely sensitive, but it's completely based on the technology that was developed by Albert Fert and Peter Grunberg in the 80s. And so, in a sense, we are always using, and I mentioned also, and finally the detectors that we are producing is covered with graphene to protect when you take this sort of sandwich into the air, so not to oxidize the magnetic part of the detector. Right? So, but still nanotechnology is too young to use this thing in a systematic way. There are some examples such as this. In most cases, you start from the very beginning.
And I will also say maybe that then, and sometimes you are working in a field of research that is really growing up in that moment. For example, I remember in organic chemistry, the molecular logic gates, that in that moment it was like a revolution, because it supposed that they could somehow be used in electronics or and we could use molecules to control circuits with and or functions and things like that. And in that moment, there were many people working on that. It supposed it would be like a revolution in terms of technology. And since I will say maybe 10 years, 15 years more or less, and nobody knows anything, or there are not many people working. Or maybe in 40 years, maybe it will work. What I mean is that sometimes you are really focused on something that is, it seems that is going to be very important. Suddenly, nobody wants to know anymore about something what you are doing, and maybe it will work in the. But definitely, I think that when the economy, when the companies are really investing in something, this is the best way in order to push some technology, or some, in this case, nanotechnology. Yeah.
But if I may add to that, this is a very important point. It also comes to your question, about in the beginning about integrating components, etc. You realize you can make a very nice nano structure or a nano component or a self-organized surface or so, but also in that field, it was very clear that to integrate things, to make a device out of it, to interface these molecules with surfaces, to make electronic contacts, all these kind of things. There are so many parameters, and it turned out to be extremely difficult, So one of the big challenges, in my opinion, is that how to integrate things to a system. that operates, you know, with multi-components, different hierarchical levels, etc. And you see beautiful examples in the institute here this morning of interfacing with surfaces to learn, how you organize things, how you organize, you know, the electronic properties, but also the orientation, the precise cooperativity, etc. All these things. Once we learn those rules, it will be more easy to make an integrated system, you know, like you have it in computer chips, etc. But still, people, I think at that time, probably did not realize enough how difficult it is, for instance, to integrate molecules with metal contacts and all these kind of things, you know. There were so many problems to solve, and that hampered the field a bit, and there were also quite a few mistakes there that people did wrong interpretations and so. But I think the field is still, there is a lot of excitement, you know, but we have to learn the rules,
Yeah, you see, the point is that there is a very basic point that was not considered by many people working in this direction, which is if you want to use molecular systems for fast electronic, how fast can you do it?
Yeah.
And how fast depends on how the electrons will move. And that, again, to go back to what I mentioned before, is because of what is called the effective mass. The electrons in a material do not move with the mass that one electron has in vacuum. It depends on the interaction and the way the bands are prepared. So in all organic materials, the electrons move relatively slow, which means that if you want to have for example, you have to have a transistor, and you want to switch the transistor from 0 to 1. How fast can you do that?
Yeah.
If you can do it 1 time per second, then forget about that. All inorganic materials, in fact, the fastest transistors are not made of silicon, are made of gallium arsenide, because the effective mass in gallium arsenide is much smaller than silicon. And that's why I mentioned the story with graphene. In graphene, in principle, the effective mass is 0. So you say, wow, so we are going to have the fastest things. But it's not true, because in that particular case of graphene, you don't have band gap.
And it's also not only about speed, but it's also what kind of complex operations you want to do. Yeah. Because this whole question about information retrieval, NOR, AND gates, etc., was a hot area, and it will come back, I promise you. We learn the rules, you know, because this whole thing about molecular information science, I think it will be a hot topic in the future.
I think so.
Think about your cells. Think about all the operations, you know, that take place in your DNA, you know, the reading mechanisms, in the ribosome, the proteins, and whatever. It's unbelievable. All these things happen in parallel. This is massive computing and information science in a complex environment. But, you know, we are already happy when we have 1 transistor, you know, and we can integrate that. So we have to learn that. Be aware, in 10, 20 years from now, there will be a lot of information science at the molecular level, in my opinion.
New question?
Okay. So first of all, thank you, the 4 of us, for being with us today speaking. I had a question for Mr. Feringa. My question was, when you started building this molecular machine, what was your first motivation or the application you had in mind when building it, and also future prospects for this molecular machine?
Yeah, very good question. Now, when we started, I mentioned it this morning, and I will mention it also tomorrow. We started with switching, you know, information storage, actually, like in your eye, information processing. And then we discovered that the molecule was not switching back, but was switching forward, under the influence of light. So serendipity a little bit, So we thought, okay, if it doesn't switch back, but it switches forward, we have 180 degrees. If we do it twice, we have a 360-degree cycle, and we make a molecular motor. And this is how it all started, And so then we thought, okay, what is known about molecular motion? And the only other approaches were the pioneering work by Fraser Stoddart and Jean-Pierre Sauvage that make these rotaxanes and so on, that moved with 2 components with respect to each other. But ours was simply propelling like a propeller. And once you realize that, then suddenly all kinds of things, the half of the world opens for you, because you can move things, And so we built all these kind of different things that move, you know, and we could amplify motion, and so we take this, I think what a cool experiment, I think I didn't discuss this morning, what my students did is they took the motor as an initiator for polymerization.
Great.
You know, you need one molecule, and you polymerize and make a long chain. But once you have a motor and you irradiate with light, it starts to move, and the whole polymer chain is starting to move, you know, it starts to invert helicity and all these things. And we were talking about swimming things, you know, objects, particles, all these things. That is what we designed with flagellas, just like a bacteria. And so there are endless opportunities. It's just your imagination, you know. And our encouragement comes from Mother Nature, yeah? The fact that I wave to you, that I can see you, that I can stand up. This is all molecular machines, yeah?
In that sense, I think this morning, do you remember when I was talking during my presentation that I said, okay, maybe you can ask me now, and why we are doing this? What's the application? And I say, no idea, but it's beautiful. But it's beautiful. Sometimes things are beautiful, and they will find an application. Somebody will find the potential of what you are doing in an application, and I think it's the part of science.
Something moves.
That's a very, very important message.
Yeah.
Don't do things in principle in science because you have an application in mind.
The applications will
Do
come.
things because it's fun, it's beautiful, it's something that...
Come with something.
And then maybe you or maybe somebody else in 20 years' time or in 3 years' time or whatever will find an application. But don't do it, I mean, it's not done this way, usually.
Yeah.
There are a few exceptions.
I fully agree with you, because I get this question often, and you know, I was so surprised. Before the COVID, I was in China, and as you can make responsive surfaces, because you make these machines on the surface, they make self-cleaning windows.
Great.
On a lab scale, of course, but imagine. I had never thought about that, yeah? But can you imagine how many people will be happy when your windows and your car cleans itself?
Well, window cleaners will not be happy, probably.
Window cleaners have no business anymore. No, but there are
become
many,
jobless. Yeah, sure.
Think about biomedical applications, you know, when you have responsive surfaces and so. Bacteria don't like that.
Yes, low-falling surfaces, for instance, there are a lot of materials, a lot of molecular machines, a lot of opportunities that you create something you are looking for, a specific property or particularly property, and in other occasions there is a little bit contribution of serendipity. Sure.
Yeah.
But you have your son, your daughter, and you have your discovery, and perhaps you cannot find the application in this moment, but I'm sure that somebody could find an application in the future. It depends.
Yeah. This morning I heard a lot of studies about this beautiful structuring on surfaces, self-assembly. This, of course, is a huge area, you know, in nanotechnology, how to organize things, also how to instruct the materials to self-assembly in beautiful patterns for certain applications. And this is so important, you know, for the future, for all kinds of new, think about coatings, think about all kinds of materials that we make for electronic applications, for biomedical applications, responsive surfaces, whatever. But also how to learn, that materials can be easily recycled, because you can organize it in such a way that they are strong, but then you can induce a way to get them deorganized again, and they fall apart and you can recycle. Or, you know, to use them for self-repair. I mean, your body, I mentioned this, if you have a scratch, you know, it repairs itself. But a scratch in your car doesn't repair itself. So, but if we learn those basic fundamental principles of how organization takes place and how things can go reversible, you can make these kind of things. And that will help us a lot in the future for new technology. Don't worry, there will be people that want to spend money on your discovery.
Let me be politically incorrect. One favorite hero of physicists is Richard Feynman. Richard Feynman was a very famous physicist that got the Nobel Prize by developing the most precise theory ever developed by human being, quantum theory, of course, and he was famous for being a bit eccentric, let me say. he had a very famous quote saying that physics, he mentioned physics, but you can change for science. Science is like sex. Sure, it can give practical results, but that's not why we do it.
Okay, so the very last two short questions, please try to make a quick answer, because before finishing, we want to ask you a question for the audience, to any of you. So please, go ahead.
Yes, so the question I would like to pose to the table is related to yesterday's roundtable, where we said that university is a place where experts talk to experts. So I would like to ask you, what do you think that is your responsibility as the leading scientists right now in pioneering investigations, and our responsibility as upcoming scientists in the field of nanoscience? Because given that it's very multidisciplinary, how do you think we should make it approachable to society? What is our responsibility to society? And because it's so multidisciplinary, how does it involve patents? I would like to know your opinion on this.
Can I answer? Maybe from my point of view, if I take myself as an example, is the responsibility is total, and I will say why. So I study at the school, public education at the school. I study later at the high school, public education. At the high school, I went to the university. Nazario was my professor of organic chemistry. You don't remember, but I remember. Also public education. I'm talking now maybe at the Spanish system, but I will explain why. So later I got some grants from the Spanish government, and I went to Germany. I was with Luisa de Cola for 3 years in Germany. Later, I came back, public money, with a Ramón y Cajal fellowship. Now I'm professor at the university. So what can I say? I have to do everything for the public research, and to try to teach and to show to the general public and to the society, the Spanish society in this case, but international, because I was a real product of a public system.
Wait to receive a strong offer from an Arabian country. Okay. This is another matter. Okay, sorry for my comment. Okay. Next question, please. Who was it? Sorry.
Hi, it's been a really interesting debate, and I really like the part of you have to do something interesting, even if you don't find an application at this point. Actually, I'm quite far from industry, so but I think we haven't talked about a particular point that always came up, and I think it's important, is when they asked if how long does it take to get to industry, to get to social. Actually, there is an important point, and it's, for example, in my field, is storage information, process, energy harvesting, all these really big challenges at this moment for physical and chemistry and material science. And it's, what point can we get to industry? I mean, how can we get to beyond silicon if all the industry is prepared for silicon? You have to invest a lot of money to get to industry develop further from silicon, because you have to change all the machines, you have to change all the expertise that you already get. So how can you get that? I mean, as far as we can find a way to go further than silicon, will it actually go to industry?
But do you mean in microelectronics in particular, or in micro?
For example, but
if you are talking about silicon, you mean microelectronics or in solar cells or in what?
Actually, in general, for example, to put perovskite solar cells, you have to change the industry. You have to use novel techniques of growing. to get to go for different transistors to, for example, memristor devices, you have to change all the industry again. For all these big breakthroughs, you have to change the industry. Is that actually viable?
Sure.
Well, innovation processes have been very well known and studied for many years in many different fields, and there are certain rules in innovation.
Yeah.
There one kind is when the industry is ready to take that small step of innovation in the massive products. So one example is this reading head that I mentioned before. IBM was completely preparing for a new generation of hard disk based on magnetoresistance of the order of 0.002%. When a new material was discovered that could do the same with 20% efficiency, then the change was immediate because everything was ready. Now, there is another way in which you want to substitute completely the thing that you are mentioning, the material that is being used in a certain moment. And that, the example, let's take a very well-known, the case of silicon in microelectronics, that now all transistors, or most transistors, are made out of silicon. Right? The technology is so well developed that they produce transistors with a gate distance of the order of 2 nanometers. In this moment, 2 nanometers by hundreds of millions of transistors, and very cheap, and that's why we have computers so cheap and all of that. So the technology is extremely mature. The investment is unbelievable to build a factory for microelectronics now that is been very important in Europe in general with all these recovery funds and all of that. The order of magnitude is typically 20,000 million euros, one single factory, right? Now it's clear that they will not change and disappear, the technology, from one day to the other. But if you take the example of a transistor, at the very beginning the transistors were not used to replace computers. Not at all. The first application was hearing aids for deaf people, right? And only after years of investment, in that case by the US Army, essentially, they were able to produce materials and transistors so cheap that they could start changing radios. It took many, many years until the transistor reached the level of being introduced into the computer. So the advice in that sense is you have new technology, try to find a niche in the market, relatively modest. Not try to replace the high-level standard in the market, because you will never get it. Right? You have to start with something.
It's very difficult to replace, of course, very well-established, excellent functional technology, like the computer chips. This is development of 70 years or so. But on the other hand, I think we in the universities, and especially you as the young stars, and in the research institutes, have the duty also to think a little bit bold and think about out of the box. Because quantum computing, molecular computing, other materials that we have not even dreamed of, there might be a lot of opportunities. It could well be that indeed there might be a quantum jump in 20 years from now that we have not even considered. And I remind always of the words of this Henry Ford. Yeah? You don't know who this is? Henry Ford, the father of the automobile industry, more than 100 years ago. You know what he said? If I listen too much to the general public or the industry, what they would have said is, I should breed faster horses so that they can run faster. Make chips that are smaller, faster horses. And then he invented the automobile, and it changed the world completely. Yeah? So this is how things go.
Okay, this is time explained, but before leaving, Rodolfo, any of you will have 1 minute, and I will start with you. Providing to this audience a landmark or a milestone or an achievement in nanoscience with having an social impact, or presumably having in the near future a social impact. Any of you think about one? Okay, so let's start with you.
I will start with
1 minute. 1 minute.
With the instrument,
Right now.
I mean, science is about measuring things, it's about instruments. And the instrument that opened the eyes of everyone in the world to the world of nanoscience was the scanning tunneling microscope. This invention created for the first time an easy way to see atoms and molecules. And that gives you such a kick in your mind that millions of people have started thinking on how to take advantage of that thing. So that's my number.
Did you think?
It's a interesting question and difficult. If I have to choose, I will say lasers. Lasers. Because you mean about something that they created a strong impact, right? So I think that
I said impact, but if you want to say strong impact, that's fine.
Yeah, I think that no, at this point, for example, the creation of nano lasers. So
please go ahead, but be careful. It was a pleasure.
So I think that the combination of the nanoscale with the fabrication of lasers, so of light with all the conditions that have lasers. Lasers are somehow macroscopic, so I would say microscopic. But if we could somehow create spacers or lasers in this small size that we can control with light, I think that the achievements that we could find they should be unbelievable. So focus on this regime for lasers, from my point of view. Yeah.
Yeah, you took the minute plus the 20 seconds from Rodolfo.
Okay.
Please go ahead.
I think that a hallmark in the case of nanomedicine has been the application of the nanovaccines for COVID. And the possibility to incorporate the nanomedicine, nanotechnology product, to save lives and to try to control a pandemic crisis that was terrible. So I think that it's going to open the mind of a lot of scientists and physicians and so on to rely on this type of technology for healthy purposes. For the health. So I think it's going to be applied in different diseases, going beyond infection, even for the prevention of cancer, I think.
Okay, thank you. And Ben?
Yeah, for me, one of the most significant impacts is molecular nanotechnology, where you can, for instance, a DNA nanotechnology, that you can modify DNA at will, engineering in a protein, any functional group that you want, put there something, to deliver a drug, to activate a drug on the spot, to change the properties, to drill a hole in a cancer cell, all these kinds of things, do a chemical reaction precisely in a biological system, molecular nanotechnology, starting with the trajectory from precise engineering. I mean, it's amazing what you can do with DNA. You can put in a new code, you express the protein, you get a hook, you can do the chemical reaction in the cell now, or on the cell membrane. You can put in a light switch like we do, and you can switch on and off a function. This kind of things, that is, I'm a molecular nanoscientist, and of course we need all the other things as well. But to me, that is a feat of nanoscience, and it will change the medical profession in the future, So I'm a believer of molecular surgery in the future, Surgeons will be robots and molecules.
That is a good topic for discussion tomorrow, because I prepared some slides related with artificial intelligence as well. So, but that would be for tomorrow, okay? Please, since you are our guest invited, Montse, Andres, I think there is no problem to give you the opportunity of telling to the students. You already did it to give some advices, but particularly for those people that they want to dedicate their lives to science, and also to maybe to make a group in future. Advices,
I gave already a couple of advices. The most important advice is follow your dreams. You are excited about science, about discovery, about invention, yeah? Please do so. And the universities, because somebody was asking about the role of the universities, and why should we put all this money and what is the output, etc. The most important, of course, is you. Because we confront you, yeah? That is our duty, to confront you beyond the frontiers of current knowledge and science. Going beyond the current frontiers of knowledge and science. Because if we train you only for today, we do already a wrong job. We have to train you for tomorrow and the day after tomorrow. Because you will there be guys that lead the science, yeah, the universities, the industry, build our sustainable society and do the inventions for the future. So never forget that, eh? We always look at the big professors, but you are my heroes because you will do it. But that means that you also should be eager and not to be too afraid. Because realize when I was a student, I didn't know exactly what to do. I was just excited about science, to do discoveries, etc., and to learn. And I think to see something the beauty of chemistry in my case, of the beauty of materials or the biological sciences. There are so many things to discover, etc. And if you are comfortable with that, yeah, go for it, and don't be too afraid that you don't make immediately a big discovery. I mean, you start small, yeah, but you can make a big impact at the end, yeah. And so be confident, yeah, and take the beauty of science with you, and you don't have to make a choice now. Is it now? Will it have an application? I don't know. We don't know, yeah. Hopefully, sometimes, but most important is that you experience, yeah, the joy of discovery, of learning. I think that is the most important thing.
Thank you. In my group, they are expert in small advances.
Me too.
Maybe in the future they will increase the size of the advances. Okay, but so far so good. They are very kind because none of them tested because to Emilio and me, because where is the guy coming from the industry, social impact? So, but unfortunately, just by fortune, we have to Ben with us, and you was around 6 years in Shell, which is a big company.
No, but can I make a comment there? I'm a chemist, and we work also on new materials, sustainable process, etc., nanotechnology, of course. During my whole career, I always had also some programs with industry. So I worked together with BASF, which is the biggest chemical company in the world, with Shell, AkzoNobel, Unilever. So on projects, that we focus on, new coatings, for instance, for paints and coatings, and so bio-based coatings, these kind of things, or responsive surfaces. But at the university, we should not forget, university should be a playground for science, yeah? And so the fundamental science is the most important, that we keep that basis. And on top of that, we build also these programs. And there's nothing wrong to work with industry. Several of my students like projects, where we also work with industry. But industry comes to us nowadays and says, do you have for us new openings, new opportunities, what we can do things different? Because they're all confronted with these questions. We have to reshape industry. We have to make new materials. We have to do sustainable things. All these kind of things, new biomedical things, etc. It's amazing opportunities. I mean, I really regret that I'm not a student anymore. Because there are so tremendous opportunities, to go for the future, yeah? And industry indeed is partner of that. We should team up with industry, but keep your own position. Universities should not become industry. Universities cannot build cars, and they should not build a factory. They should have their own mission. Yeah, that's important for me.
Some of your colleagues, me in between them, I in between them, believe that your fresh air you brought to science was probably due to the influence of your time related with the industry.
No.
You are able to see one step further for applications, maybe. So now the question and how influenced your statement? Well, you said the relationship with industry has been permanent, but you was a long time in the industry, and how influenced this your science?
I was lucky, because I wanted to do a postdoc in the United States. Yeah, I did my PhD. Hans Winberg was an American professor, and he said you should go to America, and we arranged it. And then I turned out, when I finished my PhD in Holland, army was still compulsory, so I had to go in the army, like you. And so Shell kept me out of the army. Don't tell anybody, because but, Shell kept me out of the army. But the Shell labs at that time, you probably heard about Bell Labs and so, these famous laboratories. Shell also, they had a huge laboratory, and they did very fundamental science, you know, in catalysis, materials, etc. It was for me like the catalysis university of the world. It was absolutely fabulous. I saw equipment there that I'd never seen at the university. The best tandem mass spectrometers and so, we could not afford at universities. And so it was for me, I learned a lot, but simultaneously, you know, they confront you with also, okay, is it useful for our company, you know, because they are an oil company. And I remember, I have to tell you the story, not to discourage you, but I worked for 6 months on a fantastic project, and we had really a beautiful catalytic system, yeah? And then the American, I had to give a presentation like in this hall full of all these Shell people, and the American head of research, he was an American guy from Texas, because Shell had a big lab in Texas. He came and my boss introduced me and said, now we will have a short contribution by Dr. Pirga, because he just submitted the patent, and we are very proud of what he did. I was really proud of what I did. And I could present for this big boss, you know, that was the research director. And then the first question after my presentation was, what will be our business? And I said, sir, we can produce 6,000 tons a year. No, sorry, we can produce 10,000 kilograms a year. Yeah, it was a very precious material. And then we have the world market. And this is an oil company, Shell. They start to think at 100,000 tons. So I said 10,000 kilograms and we have the world market. Dr. Ferga, 100,000 tons, do I understand correctly? No, I said 10,000 kilograms.
No, what you're saying.
Within a day the project was stopped. So you learn also about failures or about what incentives are. Yeah? You can imagine, I had a bad day, you know. They stopped my project because they said 10,000 kilograms is a rather small business. They start to think at 100,000 tons. That depends on what company you work, of course, but you have to be. I learned, to answer your question in a different way, getting out of the university bubble and to work for a few years in industry was also kind of an eye-opener, you know, and you get a more realistic perspective on application, you know, there are many questions about applications. You don't get a medicine in the hospital so easy, you know. See, no, it's a long trajectory before you can use something in a patient, or you have to go through all these phases and tests. It takes 12, 14 years, you know. And for other applications, if you have a new material, and you go to, you go to Mercedes-Benz, and you say, I have this fantastic material, can you use it in your car? Now, then you have a hard time, I tell you, because they will say, you think we should replace our factory, you know, with your material? This is an investment of 1 billion. You have to have them good arguments, you know. So, don't get discouraged, yeah? But you learn also to look at a bit of a different perspective. But we have several projects with industry, and it's fantastic, and they ask us to do fundamental discoveries. And in the last few years, we had 6 patents, you know, so I'm very proud of my students. So, be enthusiastic.
So don't miss for tomorrow the joy of discovery that this will continue. I will make a short introduction with a few slides about the machines.
Okay.
What is expected the machine for the future.
Okay.
Let's see. In the meantime, please join to thank to me, to thank to all of them. I join me to thank them for this wonderful roundtable.